Well, welcome to the last lecture for this quarter. Today we will be completing our roadmap. Specifically, we'll be starting by wrapping up our discussion on model-free reinforcement learning first, where we're looking at policy optimization methods, and then we'll discuss model-based RL. So, if you recall, basically what we were saying last time is that we started looking at policy optimization approaches for model-free reinforcement learning, whereby the main idea was to basically build these and compute these policy gradients, which are basically the gradients of the kind of ground truth reinforcement learning objective that we're interested in optimizing, which enabled us to basically derive the number of algorithms ranging from reinforce to actor-critic algorithms. And then we basically concluded with kind of having to basically discuss some more recent reinforcement learning algorithms that relate with policy optimization. And if we kind of take a step back and think about how kind of state-of-the-art algorithms in machine learning more broadly typically work, they ultimately boil down learning to a numerical optimization problem, right? So let's think back, for example, at our classical regression problem, which is described as a supervised learning problem. There we typically formulate it as a training error minimization problem, which we can optimize sequentially, taking a data set of observation until we converge to some local optima. And this is fundamentally different from what we've been doing so far in reinforcement learning. Because if we think back at value-based methods, kind of Q-learning being a prototypical example, this is, well, first of all, fundamentally different because we're not really optimizing an objective, but we're doing fixed point iteration, which can, in principle, include kind of all of the transitions from an offline data set. But from the perspective of trying to mirror this same formalism, this is not really optimizing the ground truth reinforcement learning optimization problem. On the other hand, we saw how policy optimization methods, on one hand, do optimize for the ground truth reinforcement learning objective, but we only do basically one step of gradient descent at a time, right? So we saw these how, at least nominally, these are on-policy algorithms where we have some interactions with the environment, we collect data, take one gradient step, and repeat, right? So this is really, in a way, fundamentally different from just positing this as a numerical optimization problem and kind of crunching the numbers until we converge, if that makes sense. So we'll discuss two specific algorithms, namely trust region policy optimization, TRPO for short, and proximal policy optimization, or PPO for short, which originally kind of were born by trying to replicate this sort of formalism of positing an optimization problem and crunching it until convergence for the purpose of reinforcement learning. Where the goal, therefore, will be to define a kind of a surrogate problem and have it such that we can take continuous updates to our policy before potentially grabbing new experience from our environment. And so we saw how in policy optimization, kind of what we want to do kind of at face value is to compute the policy gradient, right? Which last Monday we defined as being the expected value of the gradual pies multiplied by some quantity, which is a metric of the reward to go, right? We saw how an attractive kind of quantity to have here is the advantage A. Now, kind of the first idea is that what we would like to have is define this surrogate optimization problem, whereby if we were to take gradients of this objective function which we define, the gradients would themselves be the policy gradient, which we're interested in following. And so kind of a simple idea, which is also how you might have seen by playing with your p-sets, is that when you want to introduce, kind of concretely implement these kind of things and solve them through automatic differentiation, since we're interested at the end of the day in following this object over here, kind of a pragmatic way of doing so is to define a surrogate objective, which is a quantity that we don't necessarily care too much about in practice. But if we were to take the gradient of this objective, we would actually get the policy gradient, right? So in practice, this is how we would normally implement this through auto-differentiation methods. We will define this surrogate objective, and autodiff will basically give us the gradient of this object, which is the policy gradient, and we can follow that. An alternative kind of representation of this surrogate objective, which we might want to use in the exact same way, is what I'm referring here as the kind of loss IS, where IS stands for importance sampling, which is essentially an equivalent objective to the one shown here above, whereby rather than having this defined as the log pi's multiplied by the advantage, we have this probability density ratio, which comes from an old version of our policy pi, described by some old parameters, theta old, and a potentially new version of that same policy described by some current parameters, theta. So first of all, kind of to sanity check that the gradient that we get from these two is equivalent, just by applying the chain rule, we will see that the grad of the logarithm of a function is actually equal to the gradient of this ratio. So the gradient of the function divided by the function evaluated at theta old. And so, long story short is that these are kind of two separate surrogate functions we could use to nominally get the policy gradient out of it in the same way. However, this second one, that is the importance sampling one, has this nice interpretation whereby this objective is actually well defined even if we are using kind of collecting data according to a previous version of the policy. In this case, pi theta old. So you're probably starting to imagine how this objective is still valid in the moment where I'm updating my policy kind of multiple steps sequentially in a row. So I'm kind of diverging from my original theta old policy. And this objective is still valid in the sense that the importance sampling is kind of reweighting my probability that I give to the action with respect to my previous version of the policy. So I'm aware that I'm going through this quite fast, but the main idea is that we want to kind of reach the state where we are defining a surrogate objective, which still follows the main ideas of policy gradient. Here we're seeing two different alternatives, which are equivalent in that sense, because these are two loss functions, which if we differentiate, we'll still get the policy gradient. But this importance sampling version has this nice interpretation, which still holds when we are actually considering data collected according to a previous version of our same policy. Does this make sense? And so, of course, this this is the objective that kind of is used within the trust region policy optimization algorithm with a caveat. And the caveat, which we didn't discuss here, is that, so here we are mentioning this idea of taking multiple steps and therefore starting to diverge from our original theta old. But of course, the more we go further away, so the more we move from our original theta old, the more our estimate, for example, of the advantage will be less accurate. And the more potentially this ratio will kind of stagnate learning to some extent, right? And so what we want to do is we want to potentially take multiple steps sequentially, as we were saying, but we want to do this while remaining within kind of a neighborhood of the original policy, within which we are kind of confident that what we're doing is still meaningful. And so this is the idea of introducing what is often referred to as a trust region. This is a pretty common technique in optimization, whereby given that same objective that we were discussing before, we're now introducing this constraint, which is basically expressed through the KL divergence. That is a measure of divergence between distributions, such that we want that the distribution over action induced by our old policy, theta old, has to be closer, with kind of delta close, to the new policy, to the new distribution over action induced by the new policy, pi theta. Does that make sense? So why is this interesting? Is because, of course, there could be many possible ways of defining closeness for two policies. Maybe one more intuitive way would be to just measure distance in parameter space. For example, penalizing like the norm of the distance between the two theta vectors. But this is pretty attractive because this is directly evaluating distance in kind of policy distribution space, which is ultimately what we care about. Right? So we are measuring distance with respect to the distribution over actions induced by the two policies. So maybe the parameters vary quite a lot, But ultimately, what we care about is that the distribution induced by the policies remains similar. Yeah.
Is it that there's also expectation of divergence here? Is the tail divergence stochastic? Because I thought that metric itself.
Yeah, so this kind of depends also if you're averaging over different trajectories. So remember that this will be doing kind of an empirical evaluation of this, right? So we'll be sampling multiple trajectories over time and kind of doing empirical means instead of expectations. But this is why, yeah. So this was incredibly successful at the time, meaning it was able to be a pretty reliable reinforcement learning algorithm, especially for continuous control problems. However, it came with its own set of limitations because, of course, now we are changing from having to solve an unconstrained problem to actually having a constraint in our formulation, which complicates things. Specifically, in order to solve these problems, people usually use conjugate gradient methods, which can be tricky to implement. And empirically, this algorithm usually seemed to perform pretty weakly when we're using maybe deep neural networks, such as convolutional neural networks or large transformer networks, which was indeed one of the main kind of practical limitations of TRPO. So this algorithm was still extremely impactful because in a way it motivated kind of successive algorithms which try to simplify and remove these limitations, which is exactly what PPO actually is. So PPO in a way is a derivative of TRPO, which is trying fundamentally to answer the question of, can we replicate the exact same objective that we were trying to achieve with TRPO without having to resort to this second order optimization, which is basically entailing this more complex optimization problem that we have to solve in the constraint problem that we introduced in the previous slide. Is the setting clear on kind of this transition from TRPO to PPO? Okay. And so if you kind of look around for different implementations of PPO, most likely you will stumble upon one of these two versions. So the first one is, well, we have this constraint problem. We are saying that this is introducing some challenges, at least from an implementation perspective. Let's basically move the constraint to the objective function with a penalty through Lagrange multipliers, which then leads to an unconstrained problem. And let's solve this through stochastic gradient descent tools, as we have always done. So in a way, this is completely valid. Although I would say that the most popular version is this second version here, where we're basically trying to empirically replicate the behavior of the constraint through kind of an empirically derived equation, in a way. So we are basically introducing this specific objective here, where we are trying to replicate the behavior of this constraint which we introduced before. How are we doing so? We're doing so by, first of all, defining the ratio, just for compactness, as a small r of theta. So this is the ratio between the two policy distributions that we were using before. Of course, if we evaluate r at the old kind of version of the parameter theta, we will get r equals to 1. And the objective is comprised as the minimization between two terms. The minimization here is used as such that we are basically having that this overall objective is a lower bound of the ground truth objective of the ratio times the advantage. So we're basically picking the minimum between the ratio times the advantage and this clip term over here. So what does the clip function do? We're basically taking the ratio, small r, assuming this is the axis where we are considering small r, and we are basically saying that we are constraining it to be between 1 minus epsilon and 1 plus epsilon. Right, so if r falls within these two bounds, we're keeping the, the value of r. Otherwise, we're clipping it to, so if r theta would be here, we would be using 1 minus epsilon. if r theta would be greater than 1 plus epsilon, we would be using 1 plus epsilon. So we're basically keeping r theta in between these values, and then the extremes when we're going beyond that value. Of course, this gets then multiplied by the advantage. So you're starting to see how this is, at least intuitively, an empirical way in which you can somehow approximate this idea whereby we want to stay closer to the original policy, right? Because we are constraining, we're basically, these values are constraining the ratio r theta to be only as kind of not incredibly different from the original policy, if that makes sense. Yeah. So the point of the minimum here is that, so the full picture here is that we are interested in the gradients that we get from this objective. And specifically, we want to saturate the gradients whenever we are kind of beyond these clipped values, but only if these are kind of in a negative direction, meaning if we are moving very far away from the policy, but we are moving in a direction that is negative for performance, we want to clip it. On the other hand, if taking a bigger step would allow us to bring us closer to the previous policy, we are still enabling gradients to flow. So this minimum, I kind of advise you to maybe even just plot this and trying to see kind of case-by-case scenarios. But the overall intuition, I think, is there are two. One, this allows us to have a lower bound on the actual objective. And two, if you look at the behavior of the resulting gradients that you get from this objective, you're getting something that saturates whenever it is actually good to saturate. And it doesn't when you want to recover, essentially. Yeah. But yeah, so long story short, kind of PPO kind of is derived from the same intuitions that we were discussing before from TRPO. And this is definitely the most popular versions you will find out there. And I would arguably say that now PPO is probably one of the most, if not the most, popular reinforcement algorithm out there. Okay. So before moving to today's lecture, first of all, any questions so far? Okay. So just I want to spend just a couple of minutes really kind of driving home the main messages which we discussed so far for model-free RL. And so remember how we basically started all of our discussions a few weeks back by talking about different ways to estimate value functions, where we were originally motivated by the appealing properties of dynamic programming, where these were essentially allowing us to kind of decompose the problem over time by enabling us to have an exact representation of the value for each state at the end of our problem by just looking at the one-step propagation. And we were able to do this because we are actually able to compute exactly those expectations through the use of the knowledge of the system dynamics. And so we saw how these methods were in principle exact because we were not losing any information through this one-step expectation, but it required us to have a knowledge of the underlying MDP. And so this motivated to introduce kind of two fundamental model-free learning paradigms. Monte Carlo learning, which basically used sampling from our environment, kind of, in other words, interactions with our environment to approximate that expectation, and specifically define the update to our value function as taking a step in the direction of the observed returns. So we would sample in our environments, reach a terminal state, observe a return, and update our estimate of the value function towards that return. On one hand, this is great because it's unbiased. This is an actual unbiased estimator of the ground truth return. But it is high variance because there is a lot of stochastic sampling happening over time. And we need to reach a terminal state in order to actually sum backwards all of the rewards that we have obtained. On the other hand, temporal difference learning tried to combine ideas from both of these paradigms, the sampling of Monte Carlo, because we're still interacting with the environment, and the bootstrapping of dynamic programming, because we are updating our guess towards the one step ahead estimate of our future return. which is great because this lowers the variance because we're sampling only once instead of having to account for all the stochasticity of the possible futures. And it can learn online because we can do this update with just a single step. But it does introduce bias because we are updating the guess towards a guess. And so there are some trade-offs. Of course, we mentioned how this is true both for state value functions V, but also for Q functions. And this holds equally. Kind of the other main idea is that we saw how all of these ideas basically held through for the tabular representations, whereby value functions are just lists or matrices, and each entry in those lists of matrices is our estimate for the value function. And it holds similarly for value function approximation, whereby rather than having lists or matrices, we have a parametric function described by some parameters theta, which we can basically tune in order to better approximate these values. How do we tune them? Exactly how we were defining before these backups for the tabular case. Now these same targets, that is the return and the TD target, represent elements in a update for in-parameter space. With all of these machinery, we then looked at value-based methods and policy optimization methods as kind of two broad families of model-free reinforcement learning approaches. In value-based methods, we used generalized policy iteration as the fundamental kind of scheme in order to obtain optimal policy. In generalized policy iteration, loosely speaking, alternates between two processes. A policy evaluation step, whereby giving a policy, we estimate the value for the policy, and the policy improvement step, which on the other hand tries to be greedy with respect to the newly updated value function. And we saw kind of on-policy and off-policy algorithms, namely SARSA and Q-learning as specific examples, and how these were instantiations of that same framework. Of course, this applies also when you have deep neural nets in the picture. And we looked at deep Q networks as a specific example. For policy optimization, which we just concluded today, we, on the other hand, said that in policy optimization, we care about learning an explicit parametric policy, pi theta, with some parameters theta. And we want to optimize these parameters to kind of directly optimize the reinforcement learning objective, as we said today. And this, at a very high level, entails, well, estimating the gradient if we want to solve them through gradient descent techniques. And so all of our discussions of policy gradient fall into kind of step one here. And then we want to do approximate gradient descent using this gradient. We saw how policy gradient naturally describes this idea of trial and error learning by essentially being a weighted version of the maximum likelihood gradient. If you recall here, we were describing this idea where the policy gradient tries to basically push up the probability assigned to actions which have high reward. And so this encodes this idea of trial and error learning. But we saw how policy gradient is fundamentally doomed by this problem of high variance of the gradient itself. And so we discussed a number of different strategies to reduce the variance. Namely, we looked at baselines, and we introduced critics in actor-critic methods, and so forth. Okay, so if you wish, this is like a 3-minute run through everything we've been doing over the last few lectures, but I think it's good to kind of make sure that we are driving the main ideas home. But any questions on this? Okay, great. So, so remember that basically we were introducing this skeleton, and all of the methods we discussed so far essentially are different instantiation of this key RL skeleton, right? So we always have this generate samples step where we interact with an environment. We typically could estimate a return or a value function of some sort. So we could be having a value function approximator, for example. We'll see today how we could fit the model as well. And then we could use whatever we do in the second step to improve the policy, either through greedy policy improvement, as we were doing in Q-learning, or through gradient descent, as we were doing in policy optimization methods. And at the beginning of our kind of reinforcement learning lectures, we briefly mentioned a number of trade-offs between algorithms and ways to navigate these algorithms. But I hope that maybe before these trade-offs were, I guess, a little bit vague. But now if we actually look at those same slides again, I hope that most of these trade-offs start to make sense. So we're discussing trade-offs in terms of sample efficiency and stability. And so I think here kind of on-policy and off-policy algorithms are exactly hinting at these trade-offs over here. That is, how much is it expensive for us to interact with the environment? We looked at continuous or discrete action spaces, which could have implications in choosing value-based methods opposed to policy optimization methods. We looked at episodic or infinite horizon cases where Monte Carlo requires an episodic setting because we need a terminal state to backpropagate those values. And loosely speaking, I think we started to explore kind of this spectrum of sample efficiency, right? So we were looking at, for example, ranging from the less efficient algorithms all the way here we see kind of on-policy, policy gradient algorithms. We have actor-critic algorithms which try to leverage value function approximation to become more sample efficient. We looked at off-policy Q-learning as example where we could use offline data or data gathered from other policies, which makes it more sample efficient. And today we'll be introducing kind of some key ideas in the realm of model-based RL. But long story short is that we introduced these trade-offs, I guess, pretty vaguely in the first lecture, but hopefully you're appreciating how many of these trade-offs now are more concrete. Okay, and so let's move to model-based approaches. Specifically today we'll be starting from, introducing a basic recipe for model-based reinforcement learning. And we'll discuss the key limitations and challenges that come from this basic recipe. And then we'll start to see basically different ways of addressing those challenges and limitations, namely through the lens of uncertainty quantification. And so we'll have small parentheses on uncertainty quantification in general. And then we'll conclude with some examples as well as some more broader scope remarks for the entire class. The caveat here is that, of course, model-based RL goes clearly beyond anything that we'll be discussing today. But for today, I hope that at the very least we'll be conveying kind of the main ideas and challenges that come through model-based reinforcement learning. Okay, so let's start from introducing this general recipe. So at a very kind of fundamental level, if we knew the dynamics, that is a function that basically predicts the next state given the state and an action that we take in that state, we could use tools from optimal control, right? So basically pick a method from the first half of this class we could use, right? We have a model, we could plan through it, we could use a direct method, indirect method, basically our favorite choice. And so kind of a very simple idea would be, well, we want this object because it could allow us to use any of the tools we discussed before. Let's use interactions with the environment to collect data and examples of these transitions, and let's learn an approximate model of this ground truth dynamics. And so we could apply a strategy that looks like the one shown here on the slide, whereby we might have a base policy, Pi0 in this case. This could be random, it could be an exploration policy that is given to us from some domain knowledge or anything that we choose. And we could collect, and we would run this in the environment and use this to collect a data set of transitions, which are basically comprised of these triplets over here. Right? So we would be running our policy in the environment. In doing so, we would be seeing examples of these one-step transitions, which we can then collect to basically be examples of mapping from state and control to next state. Once we have this data set, we can then fit a dynamical model to this data through our, favorite regression or supervised learning technique. For example, minimizing some formal squared error or maximizing some log likelihood of our data. And then we could use this model to basically plan. So the question here is, would this work? Well, in some cases, yes, right? So especially if dynamics are relatively simple, for example, we could have some linear time invariant dynamics, this tends to work pretty well. And this also relates to some of the discussions we were doing on system identification, whereby if we have a fairly well understood model, if the underlying dynamics are within the function class that we're trying to fit, and maybe we only have to tune a limited number of parameters, then these tools actually work quite well, and we might hope to generalize good enough to the real system. Of course, this doesn't hold in probably the majority of cases, specifically when we're dealing with complex, potentially nonlinear dynamics, and especially in the combination of complex dynamics and high-capacity approximate models. For example, neural networks. And this is because extrapolating from observed data to, for example, out-of-distribution examples from our environment is difficult and can be misleading. So for basically the rest of this class, we'll be looking at ways to basically, or approaches to try and have this exact same formalism work in the cases where we might be having complex dynamics to learn. Okay, so why is this an issue? So let us look at like fictitious and a kind of pictorial example. So say we are in this very simple world, the agent is the black dot here on the slide, and we have an obstacle which we wish to avoid. The goal here is to go as further north as possible. So in this case, say that our exploration policy pi0 is something that explores a certain subset of the state space, specifically describing the state distribution under policy pi0, p sub pi0 of x, which is basically the subset of the state space induced by that policy. Of course, if we were to learn now a dynamical model on these transitions, which we collected through this experience, we might, and then we use this for planning, we might be doing something extremely meaningful within the realm or the states that we have observed. But the moment where we change and we go outside of the state distribution we have covered, this is obviously not the case. And so if you remember also our discussions on imitation learning, this is another example of kind of covariate shift and distribution shift, whereby basically when we use the learned dynamical model as an inner component of a planning algorithm, we're then observing a different state distribution. And so here, generalization and extrapolation across these settings is actually what matters. Okay, so what could be a first fairly heuristical and empirical way to improve the basic recipe we were describing before? So again, let's consider our 3 steps where we take a policy, run it in the environment, collect some data, use this data to fit a model, and then say that we want to use this to plan. Of course, what we could do, first of all, is to plan in a receding horizon fashion. So we know that the plan might be slightly off, or at least might be accurate, closer to our initial time, but then we might want to reevaluate where we actually are in the environment and replan. And so in this case, using a model predictive control approach might be beneficial, right? So this is a simple improvement here. But also what we could do is we could basically use the transitions that we are observing while deploying this policy to basically add them to the data set and refit our model. So in a way, we are gradually closing the gap between the state distribution induced by the original policy and the state distribution induced by this planning policy, if that makes sense. Okay, so these are indeed 2 simple steps which can, in practice, make a substantial improvement. However, I would say the main focus for today is on uncertainty quantification, and we'll see why shortly. Specifically, the reason why these techniques fail is that, in theory, what we would like to have is, well, we have a very complex dynamical model or system we are interacting with, and we would like to have a high-capacity model that is able to represent these complex dynamics in the high data regime. So we want to have high-capacity models. However, we also want this high-capacity model to not overfit to the observed data if we only have a limited set of that data. The reason why we don't want this overfitting problem is because if we then use an optimizer or a planning algorithm, for example, as we were doing in our previous recipe, to optimize over a learned model, the optimization will be prone to exploiting errors in the positive direction, if that makes sense. So visually, say that we have only a limited number of data points represented by the red dots here on the slide. Here we have two equivalent functions that fit data, but the blue one here is potentially representing a higher capacity model that is overfitting to the data, right? So it's fitting perfectly our observed data, but then it is behaving quite wildly outside of the observed data. Now, say that you are an optimizer that wants to maximize the performance from the blue model. You might be tempted to choose behavior that basically leads to exploiting the positive reward predictions under our model, right? And so I think this is a kind of a key problem here and a key tension when you want to use learned models on one hand that might not extrapolate or generalize well with an optimization that is in a way acting as a black box optimizer and could exploit errors in the positive direction. So for today, what we will be looking at is a possible solution to this problem, which is basically considering uncertainty and, loosely speaking, how certain our model is about its prediction as a mechanism to basically push against these possible flaws. Does it make sense? Any questions on this? Okay. Okay, so first of all, we're talking about uncertainty estimation, and what do we mean by uncertainty on the predictions of our model? And specifically, we mean what we mean by uncertainty is we mean an expression of a distribution over possible outcomes. So, for example, instead of predicting a single point estimate of what is the most likely next best state from given a state in a control, we want our system models to predict a full distribution and associated likelihood of what is most likely to happen in the future, if that makes sense. So visually, what we want from our dynamical model is something that gives us kind of a range of possible scenarios that we could be optimizing for with the associated probability. We want this because this essentially allows us to reason in terms of expectations under our model. So why is this? Why can this really inform planning? So consider again this simple example where we are the black dot on the slide. We want to reach a goal state represented by the green star, and we have this kind of cliff-like environment where kind of the lines here represents the edge of the cliff. So if we go beyond this, episode terminates, essentially. Now, say that we have two candidate open loop trajectories. So we basically assume we have access to U1 to UT prime and U1 double prime to UT double prime. And say we want to use something along the lines of the model-based algorithms we were using before, we would basically be kind of simulating in our head these two possible action trajectories, open loop trajectories, where one would lead us kind of to very close to the goal, and one would lead us a little bit more further away. In this case, the circles represent kind of our estimate of how certain we are about where we would end up. In this case, kind of in both cases, we are fairly certain about where we're ending up. And so it is clear kind of that the trajectory associated with the yellow circle is better, because it then allows us to be closer to the goal. However, kind of despite having, in a second case, assume that now we have broader uncertainty bands around our terminal point, despite the terminal kind of the best, kind of the expected value being the same in both cases, now we have a greater uncertainty over those. And so the expected reward under this higher variance prediction will be lower for the yellow circle, right? Because under this new uncertainty bound, we are actually considering the case that in actually the majority of the cases, we are ending off the cliff, if that makes sense. So the reason why we care about uncertainty estimation is because assuming we are able to do this, so we're able to learn a model that gives us an estimate of how certain we are about our prediction, it gives us a mechanism to express performance as expected reward under our model. Any questions here? Cool. Okay, so the next question is, how can we model uncertainty? We say we want to do this. What are different ways of doing so? So the first idea is we could use the output entropy from our given model. So again, kind of pictorially, what we are trying to do is we are trying to learn a parametric function which maps from states and controls to probabilities over next state. In order to do this, we might be fitting either kind of, depending on whether the state space is discrete or continuous, we might be fitting either a categorical distribution over next states. So we're assigning a probability to each of our possible next states. Or we might be fitting a continuous distribution, say a Gaussian, which basically expresses the mean value of where we expect to be and a standard deviation and a variance of our uncertainty. In this case, of course, we could use the entropy that basically comes from the definition of the distribution itself. For example, we might be using the standard deviation of the fitted Gaussian. However, model entropy is different from what is often referred in literature as epistemic uncertainty. So you might have heard about this distinction before, which is basically the distinction between aleatoric uncertainty, that is the noise that is intrinsically related with the process that we are observing. For example, here on the slide, we see this kind of parabolic process. We have some observations of this process, and there is some inherent noise that might be observed from this process. The other type of uncertainty is epistemic uncertainty, whereby we are actually uncertain about the model itself. Right? So here we were certain about, for example, the specific parameters of this parabola. It's just there was some inherent noise that is impossible to model. On the other hand, again, using this kind of fictitious example over here, we might have two possible alternative models, the green one and the blue one, which with associated different parameters, which fit equally the model, the observed data, but are just two different models. Right? So here we want to have two different values of the parameters theta that describe these two different curves. And so this is an uncertainty on the model itself. So which of these two realizations of my parameters is actually the one that is better representing my data. So using the entropy gets us some way along this path, but it clearly does not account for what we actually care about, which is the potentially mutually coexistent and alternative explanations of the data according to different models. Okay, so how do we model for this how do we estimate for this model uncertainty? I would say probably the most common approach for doing so is leveraging Bayesian statistics and Bayesian approaches, whereby typically what we are interested in doing with Bayesian approaches is that we want to basically express this model uncertainty as a distribution over parameter values, theta, given the observed data. Right? So until now, when we were discussing kind of fitting a model to our data, we are often just saying that we would be converging to a specific value of our parameters theta. Right? On the other hand, if we are uncertain about the model itself, we might be interested in modeling maybe a full distribution of how certain we are about what the real value of the parameters theta is. And so this is what we mean by the distribution over parameters given the data set. That is, we are given some observation, and we want to ideally model the full distribution of plausible hypotheses. Why is this useful? It's because once we have this full distribution, we could actually predict through our learned dynamical model by basically averaging out all the possible future predictions that would happen if we were to basically average out over this full distribution. And so this is referred to as the predictive posterior distribution. Formally, this is expressed through this integral over here, where we're basically saying that we're computing the prediction of our next state, averaged over all possible values of my parameters theta. I think, you know, as often the case, to visualize these integrals is often useful to see this in the discrete setting. So say we have only two values of our parameters theta. This integral, this predictive posterior distribution would essentially entail running my predictions for both of my values of theta, and then weighting the prediction based on the probability of each individual theta. This is the continuous kind of expansion of that same idea. How does this look in practice? Well, of course, we won't have time to cover this here, but you know, Bayesian statistics basically provides, and the Bayes theorem provides basically a mechanism to retrieve the posterior distribution over parameters from data. But let's look at what this means in practice. For example, say we want to solve a regression problem where we have some we have an x, so we want to predict the value of y given x. We want to fit here just a line to this data, so we have two parameters that we want to fit. So the intercept and the slope. Say that we have only one observation from our ground truth process, which is the dashed line over here. If we fit our linear model to this data, of course there could be many possible, well, in principle infinite lines that pass through the point, which in practice would mean we would have a very broad uncertainty over possible values of our parameters, represented by this plot over here. So here we're plotting the two parameters, say the intercept and the slope. And so we could see that while the ground truth parameter is represented here by the red cross, our posterior distribution is still pretty broad. What does this mean in practice is that if we were to sample n realizations of my posterior distribution and plot the line, you would get these different red curves. If we would then average out according to the predictive posterior distribution, we would get these confidence bounds that we have on the right. Are the plots clear? Yeah. And so what we're showing here is the basically progression as we collect more data, right? So here we were looking at the case where we had only one data point. Here we have more data points, and so our posterior distribution of parameters is more narrow and closer to the ground truth. And you see how the overall uncertainty bounds that come from the posterior predictive are also more concentrated. Until here we are observing enough data to have a pretty reliable estimate of the ground truth model. And so, given that this is clear, let's briefly mention a couple of, I would say, the most popular approaches for modeling dynamical systems in a way that we are accounting for this uncertainty. And we'll be looking at two. The first one is Gaussian processes, and the second one is ensembles. So a Gaussian process, loosely speaking, is basically represents a distribution over functions, right? So you could imagine that if we are sampling from a prior distribution over functions, that is before observing any data, we will be getting pretty different behavior. On the other hand, Gaussian processes basically formalize analytically a mechanism to go from a prior distribution over functions to a posterior distribution over function in light of observed data, which would basically be still a distribution over function that is consistent with the data at hand. When I first approached also Gaussian processes, I would say one of the most confusing aspects to me was this idea of distribution over functions and what actually meant. In practice, Gaussian processes model data as multivariate Gaussians. So this is why they're referred as Gaussian processes. And basically encode this idea that an n-dimensional Gaussian, for example, a two-dimensional Gaussian, can be mapped, so a sample from a n-dimensional Gaussian can be mapped to basically an approximation of a function. So say that we are sampling from this two-dimensional Gaussian, say this point over here, which could be like 5 and 4. Now we could take this kind of two-dimensional, basically vector which we just sampled, and if we plot it kind of still in 2 dimensions, what we could get is that we could get a first value of 5, a second value of 4. And by connecting this, we're basically getting discretization of a function now described only in this small interval. Now, of course, we can only plot things in 2 dimensions, so maybe this might not yet look like a function to you. But now imagine that we are sampling an n-dimensional vector from a multivariate Gaussian. Here we would get just a vector with more numbers. And if we still plot them in the same way, we would basically get the expression, the approximation of a function, right? So this is usually what, how these are implemented in practice and why people refer to these as distribution over functions. In practice, you can imagine that Gaussian processes essentially provide a mechanism to update from a prior distribution over functions to posterior distributions once we have observed data. Again, we're kind of sticking to intuition, but I hope this is making sense. Yeah. Mm-hmm. Yes. So here I was trying to provide kind of an intuitive understanding of what people refer to as distribution over functions. So a Gaussian process is essentially representing a multivariate Gaussian distribution. So it's, for example, here I was representing it in 2-dimensional. So if we have this 2-dimensional Gaussian, a sample from this 2-dimensional Gaussian could just be this point over here. Here I was imagining like 4, 5 as coordinates. If we would be wanted to plot this point as a function, essentially, this would essentially be something like this, where we are basically mapping this point and these coordinates of this point, but just unfolding it into a function, if that makes sense. Now, the intuition is that what happens if I want to build, like a full continuous function as we were doing before? You could imagine that it's basically a more finely discretized version of this with an n-dimensional vector, right? So if rather than having two-dimensional Gaussians, I would have an n-dimensional Gaussian, say 100, then we would be able to basically represent points on a very fine grid. And by basically plotting these points, you would get a function out. Yeah. Yeah.
Estimating values of the function. Or is it does it have to be the sequence of numbers that the function would output?
Yes, so maybe to rephrase what you're saying, here we are implicitly assuming an order of the dimensions. Yeah. But from the perspective of learning, this doesn't really change anything because we are still fitting kind of the Gaussian that we are learning to a high-dimensional object, right? So for us, kind of data will be living in this high-dimensional space, and we're just fitting a n-dimensional Gaussian to that data. This is just the way we would then plot it. Yeah. Okay, so why are Gaussian processes popular? First of all, Gaussian processes are extremely data efficient. And they provide an analytical expression for the exact posterior, that is, the exact posterior over functions described by your data. Meaning, given some data points and some assumptions on Gaussianity, this distribution is actually the exact representation of the posterior distribution over functions that explain this data. This is pretty cool, because if we wanted to achieve something similar with neural networks, this would be very hard, especially with this amount of data. Because this is an extremely low data regime, and so getting these extremely well-behaved confidence bounds is very challenging to have. On the other hand, Gaussian processes achieve this by having an exact representation of the posterior. On the other hand, I mentioned analytical expression of the posterior. This analytical expression, at least in the nominal case, entails having to do some matrix inversions. And so depending which, as a function of n, where n is the number of data points. And so scaling Gaussian processes to high-dimensional data is actually complex. And so there are extensions of Gaussian processes that try to do so, but at least in their kind of at face value, this is definitely a weakness. Okay, a second approach for estimating uncertainty is referred to as bootstrap ensembles. And the idea is that, so we have this general mechanism for learning dynamical models through supervised learning. That is, we just fit a black box model to our data. And we want to have encode an idea of uncertainty in this estimation process. So what we can do is that the idea of ensembles is let's train multiple models and see if they agree and where, with the underlying idea that these different models different models trained independently to fit the same data will likely agree when they are certain about their predictions, and they will likely disagree whenever there is uncertainty. Right? So say you have n versions and copies of the models that have been trained independently. If they will be probably agreeing close to the regime of observed data, and they will potentially disagree when we are going far away from our data. And so ensembles basically instantiate this idea through an algorithm, which is basically saying nothing else that we're saying here. In ensembles, you would just train independently n copies of your model, and then average the prediction according to these n models. So specifically what you would be doing is, say we have 5 different neural network models which we train. We could then get 5 different predictions for our next state. And so what we can then do is maybe our prediction would be the average prediction across these models. This could be one idea. And maybe another way to visualize this is, say that we have, so here the x-axis represents the parameter space, theta. And the y-axis represents basically this is the posterior distribution over parameters given data. So say that the ground truth posterior distribution is represented by the shaded kind of multimodal distribution here. And for now, disregard VI, which stands for variational inference, and this multi-swag algorithm. The ensembles would essentially mean, in this case, fitting 4 different models, the blue ones, independently. Through optimization, these 4 models will converge to 4 different values of the parameters theta. And so these parameters theta might converge to different local minima, depending on how the optimization goes. And so these are essentially an empirical approximation of the ground truth posterior distribution, because they will naturally, because of the stochasticity of stochastic gradient descent and the optimization process, they will converge to different local minima. And so these are a way of empirically exploring the landscape and approximating the ground truth posterior distribution. Yeah.
Differences between the different ones, because the goal here you have a multimodal distribution of data, right? Your goal is to figure out what all the modes are by having just each one of these. You said neural nets as an example. Each one of these represent a different mode that you hopefully can figure out the instructions.
Yeah, indeed. So the idea here is that this learning problem very likely has a highly multimodal landscape of solutions. The approaches we were discussing before, like Gaussian processes, try to derive analytical expressions for these exact distributions. Ensembles here, on the other hand, disregard any of this formal approach and just decide to instantiate n copies of these models, maybe initialize them differently. The stochasticity of gradient descent still will lead them to converge to different final solutions. And by doing so, the hope is that they will cover meaningful different modes of the ground truth posterior distribution. So I think the original question is, how do you differentiate between these copies? I would say, if we're talking about neural networks specifically, typically these models are initialized randomly. So the initial values of the parameters are random. And also we're optimizing them to stochastic gradient descent. And so even the directions that they're following will be random to some extent. So there is some natural stochasticity that comes.
Different set of parameters. And then also why direct distributions? This might just be because I forgot what direct distributions.
Yeah, no, indeed. So this is something that I did not discuss. So the idea is that formally, so I think hopefully in practice it makes sense what we're doing, right? So we're initializing 4 models, and then we have 4 different converged parameters theta, and then we could average over them. What are we doing in practice is that we are approximating the ground truth posterior distribution by taking the average of what is referred to as a direct distribution, which is essentially saying that, say that I have one observation of my theta. The direct distribution is something that is basically a spiky distribution that gives all the probability mass exactly to that point. And so this is, if you wish more formally, how this process of averaging out predictions from different models would translate to the predictive posterior that we were describing before, through the lens of these direct distributions. So remember that in the predictive posterior, what we are saying is that we want to average out over all the different models that we're training, or specifically average out over the posterior distribution of our parameters. So do you remember the discussion we were doing on predictive posterior and what that means? How do we compute those confidence bounds? Is that we were basically, for each, in the discrete case, for each value of our parameters, we were basically predicting with that value of the parameters, and then weighting that probability, that prediction with the probability of how certain we were of that specific value of the parameters. In this case, we are doing so not in the continuous case, but through these kind of Dirac approximations. But does that make sense? Okay, but so long story short, what we've been doing so far is that we introduced this basic recipe for model-based reinforcement learning, namely some version of run a policy in the environment, collect transitions, fit a model to those transitions, and then use that model for planning. We motivated how uncertainty, or at least estimating uncertainty on those predictions, is likely very important. And now let's look at some specific examples and how we could make this work in practice. So, how can we make use of this additional knowledge we just gained? Specifically, one mechanism to do so could be the following. So let's assume that we have a candidate action sequence, again, some given to us by some planning algorithm. And now we have an approximate model of the posterior distribution of a parameters theta, which we learned through, for example, one of the methods we discussed today. So we could sample a specific value of our parameters theta from this posterior distribution. And we could now propagate the learned dynamics through this specific instantiation of the dynamical model. We could then use this propagated trajectory to compute a predicted reward. So we're basically simulating in our head what is happening. We are given a candidate action sequence. We are sampling one of the models from our posterior distribution over models. And we're using this to propagate forward what is happening and scoring the quality of what is happening. And then we can just repeat these three steps to basically compute the average reward according to our learned posterior distribution, right? So specifically, we would be, so what this algorithm is doing is directly instantiating this idea that we were describing pictorially over here, right? So in the plot there, we were saying that uncertainty gives us this mechanism through which we can compute the expected reward under our model. And so in this way, we could basically approximate the expected reward under all of our predicted samples. Does that make sense? Maybe, again, more visually, what we're doing is that we are given a candidate action sequence. We sample maybe one version or one parameters from our posterior distribution, and we propagate the model forward. Here, we would be reaching a specific sum of rewards over time, according to this specific model. We could then sample a different version of that model, and we could have a different propagated trajectory with a different reward, right? If we repeat this multiple times, we would then have n of these propagated futures. And so what we could do is that if we average them out, we would then be computing an approximation of the expected reward under the uncertainty of our model. Okay, so of course, one thing that I really want to make sure that, to convey is that this is obviously just a choice, right? So we're not, kind of the takeaway here, I think, should not be this is the best way to go for when you're talking about model-based reinforcement learning, because ultimately it depends on the problem at hand, right? So maybe there is even no need at all to look at uncertainty quantification, because just having your linear time invariant model is well estimated enough, and so there is no need to do any of this. But in the general case where system dynamic approximation is challenging and you want to use high capacity models for approximating our dynamics, uncertainty plays a big role. And so this could be one instantiation of this idea of let's use whatever favorite way to estimate posterior distribution over parameters of our model, and then use this to meaningfully represent expectation under this uncertainty. And so just to repeat myself, this is only a choice, but it's one instantiation of this more general idea. That is, whenever we want to plan through a learned model, we might be interested in evaluating the expected reward under the learned model. So a particularly impactful paper, now a few years old, but that uses exactly these ideas, introduces algorithm called PETS, whereby the main idea is that they were using as a model basically an ensemble of neural networks to approximate the posterior over the model. They were then using sample basically different models from this ensemble and use them to generate predictions of different futures, exactly as we were saying in the previous slide. And then they would be using this in a model predictive control fashion. So they would basically have a cross-entropy method to generate these candidate plans. Through these exact same algorithm which we just described, they will basically take these candidate plans and score them according to samples from these ensemble of neural networks, and then pick the best action based on that, and implement this in a receding horizon fashion. So you predict a full plan, you actuate only the first step in the plan, and you repeat this process. And so this is just a quick note, but it's something that I think it's this is a nice paper if you want to read about these models in practice. Okay, but does it make sense how this is like one instantiation of what we're saying? Okay. So in this paper specifically, and I'm using this as an example to highlight the classical benefits of model-based RL. Is that here they would be measuring performance of, well, their method in blue compared to, well, a bunch of different baselines. But for example, they're comparing against PPO or soft actor critic, which is also a version of the actor critic methods we discussed in class, across a number of different tasks. And I would say the most interesting result here is that these model-based methods, namely the blue curves, generally are much more sample efficient. So if we compare the performance on the y-axis in general with respect to the number of time steps through which they had to interact with the environment, you could see that maybe the performance at convergence is fairly similar. But the blue curves typically tend to converge to this, converge performance much faster. And this is because through learning the model itself, we can basically circumvent a lot of the interactions with the environment. So generally, the benefits in model-based RL often relate with sample efficiency. Okay, so any questions before wrapping up the class? Yeah.
What's your favorite method?
So I like to be fairly, agnostic and pragmatic, depending on the problem at hand. I would say that. No, you're saying this is the diplomatic answer. No, I would say that the model-free algorithms are definitely more mature as a technology. And so I would say algorithms such as PPO and soft actor critic are typically the way to go for continuous control. Model-based RL is still a very active line of research. So if I have to pick one, I will go for soft actor critic or PPO. Yeah, well, there's a two, but those two, yeah. Yeah, so I think this is a nice leeway into kind of basically what I wanted to discuss here. Because throughout this class, we have been introducing, n different ways of behaving when looking at optimal control, right? So ranging from open loop methods, it could be indirect, closed loop, dynamic programming, reinforcement learning, imitation learning. And so the question that you could ask is, I mean, this is great, but you're just confusing me. Now I have to pick among hundreds of these algorithms. How do I navigate this? And the point here is that these methods are not in competition with each other, but they're actually, well, different methods will be tailored to different applications. And actually, most of the time, these methods are combined with each other. And this is because the decision-making pipeline is typically organized as through a hierarchical structure. Specifically, if we were to decompose this hierarchical structure, generally we would start with having a model of the world or a representation of what is interesting for us. For example, take the case of autonomous driving. We might have some maybe semantic maps of what we are observing in our environment. And given whatever representation of the world we are interested in, we would then have kind of the autonomy stack is typically decomposed through different modules that interact with each other. So the first kind of decision that you have to make is typically some higher level goal for our system, right? So we are perceiving the world, and now we have to choose what we want to perform. Specifically, these high level decisions might be kind of continuing the autonomous driving example, something along the lines of picking if I want to change a lane or not. So these very high-level actions and decisions that we want to make. At this level of the hierarchy, this is typically where methods that belong to kind of closed-loop dynamic programming like algorithms lie. And this is because for these higher-level decision-making aspects, we typically want to encode stochasticity and want to make sure that we are dealing with this stochasticity when picking decisions. And the output of this is typically in a form of a goal, for example, lane change. Now we have this goal, but we have to make it actionable, right? So we want to make this such that we have an actual trajectory which we can enact in the world. And so this is something that usually is dealt with open loop techniques. So we would have this higher level goal, like a navigation goal. And then we want to translate this navigation goal into a finer grained trajectory, which we want our car to follow. This trajectory obviously encodes some notion of the dynamics of the vehicle, despite this might be maybe some lower fidelity models of the dynamics. But still, we want to encode some constraints in terms of safety, some constraints in terms of dynamics. And so this is where open loop techniques typically fall. Once we have a trajectory, we want to make sure this is physically tractable and implemented on the hardware, right? So this is where usually ideas from model predictive control, specifically in its tracking instantiations, come in place. So we would have a reference trajectory that is given from the open loop algorithm. And now we want to make sure, first of all, that we're tracking this over time, but also potentially including finer grained dynamical models of the system, maybe some safety oriented constraints, which we were avoiding in the open loop stage, and so forth. So we start from representation of the world. We use higher level decision making to have a high level goal for our system. We compute a trajectory that tries to achieve that goal. We then want to implement this trajectory in practice, so we want to make sure we are tracking it. And obviously, last but not least, we feed these to the actuators, right? So at the end of the day, we have to make this work on the real world hardware. And so we want to make sure that this is actually tracked by what is happening in reality. And so this is usually where things like Ph.D. controls come in place. Of course, throughout all of this, we might have some safety concerns, and we could be dealing with safety critical applications. For example, in the case of driving, we might have some set of states which we do not want to visit because of some safety concepts which we care about. And so the safety concepts which may be computed through things such as Hamilton-Jacobi reachability are typically mechanisms through which we can inform both or either of open loop and the tracking module. So in a way, I hope this is starting to make a little bit more concrete what I mean when I say that these techniques which we introduced in this class are definitely not exclusive, but actually typically combined in an autonomy stack. And the details of these algorithms will obviously depend on the application. But so we hope that with this class, we gave you, first of all, a broad understanding of all of these concepts, and also focused on the kind of higher level understanding of how these modules could be combined and the pros and cons of these ideas. All of this is obviously we should, I think, concretize this in a moment in time where learning-based and end-to-end approaches are definitely becoming more and more popular. And so I would say that historically, learning has started from the higher levels of this abstraction. So perception is the first kind of situation where learning basically became the de facto standard. And I would say that right now, kind of end-to-end approaches are more or less starting to carve their way down along this hierarchy. I would say right now they are basically somewhere over here, so in between the open loop and the kind of closed loop trajectory tracking stage. I would say even the most bullish, companies or approaches that claim, end-to-end approaches, typically they don't mess with the lower level components. And this is because here it's really where you want to make sure you have fine-grained control, you're encoding hard constraint guarantees, and making sure that everything works concretely in practice. Okay, so if there are no further questions, I want to really thank you very much for sticking with us throughout this quarter, and wishing you best of luck for your exam.